All right, today we're going to be talking about gravity, motion, and Newton's laws and momentum. This is part of Unit 5. All right, so this is Isaac Newton. You probably have heard of him before, or at least you should have. So he's probably one of the greatest scientists or mathematicians that has ever lived, and he is the reason we have so many things today in science. So he was the first person to hypothesize that force would pull an apple to the ground in the same way that the moon is pulled towards the earth and stays in orbit around us, which is something we use in today's modern world every day. So Isaac Newton was the first person to actually do an extensive study on the topic of gravity. And with this, he learned that gravity is the force that would attract all objects towards each other, which we know to be true today. It is currently measured in newtons because of Isaac Newton. That's where it gets its name, and it's going to have the symbol of a capital N. This is an example. So it shows in the first image 1 million kilometers. In the second image, it shows 3 million kilometers. And then it talks about how the distance between the second two objects is 3 times larger than the first. So you have the length of 1, then you have 1, 2, and 3. Therefore, the attraction would be 9 times smaller than the attraction in the first two objects because you move the 3 million kilometers away. All right, gravity is going to have the greater the mass, the greater the force. So similar to a lot of other things in life, if you're looking at something that's strong and has a heavier mass, it's going to have a heavier force. If I throw something that's heavy into a pool, it's going to have a bigger splash. That's the same kind of idea here. In retrospect, though, if you compare the opposite, the greater the distance, the less the force. So the further objects are apart, the less distance and less force they have together. In saying that, we would mean things like Mercury would have a greater gravitational force to the sun than Neptune would because the orbit is much closer. Example here, 10 billion kilograms, 1 billion kilograms, 10 and 2 billion kilograms. The attractive force is going to be in the second image twice as strong because we have 2 extra billion here as opposed to the 1 billion in the top. All right, so gravity and acceleration basically indicates that objects are going to fall to the ground at the same rate. That's because acceleration due to gravity is going to be the same for any object in the world. This is a stop motion photo. On the left side, you have a ping pong ball that is blue. On the right side, you have a golf ball that is white. If you know anything about ping pong or golf balls, you'll know that the ping pong ball is much lighter than the golf ball is itself. They do have different masses. Even though they have different masses, you can also see that they pretty much fall at the same exact acceleration point and rate. So with that being said, all objects have an acceleration of Earth as 9.8 meters per second, or 9.8 m/s squared. So basically what that means is every meter that it travels per second is actually not going to travel 1 meter, it's going to travel 9.8. So in the image here, you'll notice at 0, when he first lets the object go, within 1 second, it's traveled 9.8 meters. Then 2 is now 19.6. So on, 29.4 to 39.2, all the way to 49 at the bottom, indicating that every meter per second is going to increase by 9.8. And that is always a standard rate and a number you must know. All right, which leads us to air resistance. Resistance is going to be the reason objects do travel different speeds, such as a feather and a ping pong ball. They're both very lightweight, and we just said that the acceleration point of 9.8 meters per second is the same. However, resistance is going to oppose those forces and cause them to fall at different exact speeds. So we have 3 things in this image. We have the force of gravity pulling the apple down. If that was the case and only the case, then it would accelerate at 9.8 meters per second. But we also have the force of air resistance, which is pushing up on the apple. And because of that, the force has to be subtracted from that force of gravity. When you do that subtraction piece, then you end up with your net force of the motion or the movement by itself. In this case, because the net force is not going to be 0 newtons, the apple's going to accelerate downward. If it were 0 newtons, then it would not be in motion at all. All right, so in this image, a vacuum is a place where there is no matter, there is no vacuum resistance or no air resistance within it, which means objects are going to be in free fall. When an object is in free fall, it's just in motion because there's nothing in there to create a different movement of speed. Therefore, the feather and the apple fall at the same pace. Terminal velocity is the constant velocity of those falling objects, and they're going to be when gravity is balanced by the air resistance. Something to think about would be the brain pop that we watched the other day of Tem and Moby doing their parachute jumping out of the airplane. All right, which leads us to Isaac Newton's first law. The first law of motion is one we talked about in 6th grade, and basically it says an object at rest will remain at rest unless acted on by an unbalanced force. It also indicates that an object in motion will continue to be in motion in that same speed and that constant same state of direction unless something acts upon it in an unbalanced force, such as in this image. The skateboard is constantly moving to the right until it encounters the object on the ground. When it does that, that's when the unbalanced force becomes present, and that's when the motion ceases or stops and the little character falls off. So this is also known as the law of inertia, and inertia is also the law of laziness. We did talk about it extensively in 6th grade, and you should remember. But in case you've forgotten, the law of inertia states the tendency of an object to resist a change to motion or in motion. It's also why, as you would see in this image below, that you would wear your seatbelt. If you didn't and you crashed in a convertible, you would fly forward because the inertia would stop the car, but then you would have that moment where you continue moving. Hence, the seatbelt pulls you back. All right, some other examples of the law of inertia. If you look up here, this would be one of a magician's trick where they pull the tablecloth out and the dinner plate and the silverware remain in place. We also have another one here where we would have you ride a horse, similar to the car example. The horse stops, but you go flying forward because you're still in motion. We would have the car turning left where you appear to slide to the right, or the car turns right and you appear to slide to the left. The difficulty of pushing a dead car, if it's not in motion, it's not got any kind of movement available, to move it in itself is very challenging. And then, of course, the football player running with the ball. So that leads us back to the 6th grade topics of why do the Earth and the Moon remain in orbit? We've talked about gravity and inertia, but they work together to create centripetal force. We did that lab in 6th grade. Inertia is going to be where it is just straight going in forward motion. It's continuous. It's in that same pattern following the first law of Newton. Gravity, however, is going to combine and it's going to pull that object in. So when you would start something on a straight path, it's then going to curve because it has that gravitational pull. If it didn't happen, then there was no gravity, then inertia would just cause the moon to keep going, the Earth to keep going in regards to the sun, and so on and so forth. If it only gravity existed, the Earth would then be pulled into the sun or the moon would be pulled into the Earth. Together, they work together to create centripetal force. Here's a visual showing that. We are pulled towards the sun by gravity. The moon is pulled towards us, but if you notice, it's in a circular motion because of that gravitational pull, but the moon otherwise would be going in this straight path and continue off the page. Orbiting as an object is when any object is traveling around another object in space, such as this spacecraft. The spacecraft is moving forward at a constant speed. That's inertia, continues to follow it, never moves. It's also in free fall because gravity is pulling it towards the Earth. It would continue to move straight down if it weren't traveling forward in that free fall motion. However, because they work together, it's actually on this orbital path and it's going through the space orbit itself. Astronauts in space appear to be weightless, but they are not because they are technically in a free fall. And because of that, that's why it appears that they are floating, but they technically are, quote, not. Just a little recap, a body at rest wants to stay at rest. This is Newton's first law, unless it's acted upon by some unbalanced force. Just remember, it's the law of laziness. You want to be lazy and take a nap. And this is our favorite image all the way back from 6th grade here. Inertia, your truck has brakes, but the stone does not. It's continuously in that forward motion, even though the truck has come to rest and has stopped. Objects do not always stop in the same time. Same idea going back to the car, you being thrown. That's why you wear a seatbelt. Same idea going back to the horse, where the horse would throw you off, and that's why it stops, but you still continue moving. So that is inertia and gravity and Newton's first law. There are videos embedded in the PowerPoint. If you want to go back and view them on your own, it would be a great idea to review. This video right here is a fantastic one too.